Hello everyone, and welcome back to a new episode of Advent of Code. So last episode we did day 9, and as you can see, I've done day 10 already. It was just more convenient to do on my own than to record it, and it took quite a while, so much of that time was also not very interesting. So we're going to just go through and give you a tour of what I came up with and some thoughts that I had on the matter. Day 10, not hash. You come across some programs that are trying to implement a software emulation of a hash based on not tying. The hash these programs are implementing isn't very strong, but you decide to help them anyway. You make a mental note to remind VLs later not to invent their own cryptographic functions. This hash function simulates tying a knot in a circle of string with 256 marks on it. Based on the input to be hashed, the function repeatedly selects a span of string, I guess is a better way to emphasize, brings the ends together, and gives the span a half twist to reverse the order of the marks within it. After doing this many times, the order of the marks is used to build the resulting hash. Now, reading this, I had a terrible time, I could not understand really, what this process was describing by looking at this diagram. If you guys can, more power to you, but the next section is where they explain, with actual, with a better abstract, I'm not sure if this is more abstract or more concrete, right? It's just talking about numbers rather than objects, and so in that sense it's more abstract, but I don't know. It feels more concrete to me, because trying to understand what is going on here is very confusing. To achieve this, begin with a list of numbers from 0 to 255, a current position, which begins at 0, the first element in the list, a skip size, which starts at 0, and a sequence of lengths, your puzzle input. Then, for each length, reverse the order of that length of elements in the list, starting with the element at the current position. So we have a position that we're tracking within this loop of string, and we read lengths, and every length we read means reverse a subset of the list, starting at our current position, moving forward that many items. Reverse that subset of the list in place. And then we move the current position forward by the length plus the skip size. So past all the elements that we just reversed, and also then skip over some number of items, which is the skip size. And the skip size increases by 1 each time we do this. So the list is circular, which is easy enough to understand, but they explain here, if you try to do things beyond the end of the list, then just sort of wrap around when you get to the end and go back to the beginning. And they give an example here. If we start with 0, 1, 2, 3, 4, then of course we start like this, pointing at 0, and we read a 3, our first input. We take the subsequence of length 3 starting at the current position and reverse it to 2, 1, 0, like so. And then we move forward by 3 to here. 3 plus the skip size, which is 0. And then we increase the skip size by 1. And we do this many times. Okay. The standard list size is 256. We will never get any... That's not part of our puzzle input. That's part of the problem statement. And then our puzzle input is... well, it's a list of things. I'll show you. Oh my gosh, where's my puzzle input? Here we go. Don't skip. Don't look. Don't look. That's part 2, guys. All right, here's a fairly short sequence of lengths, right? Cool. And of course, I've already downloaded this since I've solved the problem already. Excuse me, I'm back. As I was saying, I have already downloaded my puzzle input. And in fact, since I had some trouble in, I believe it was the last episode, with getting my puzzle input safely over the SSH tunnel through copy and paste, I have just written a tiny little program that just downloads my input file using the same cookies that my browser has, and apparently a session lasts a month, so this should be fine indefinitely for the rest of the year anyway. I'm not going to show you because it has my session cookie in it, and I don't want you guys pretending to be me. But anyway, I have it, so it should be very easy to get my inputs in future. Okay, so great. Now, how do I write this program? Let's start where I wanted to... This is where I spent most of my time. The rest of this is all pretty boring. We want... The whole focus of this algorithm, like what is the hard part of this? It is implementing the twisting thing, right? Where you take a subset of a list and you flip it. The rest, keeping track of where you should flip, keeping track of what the string is in between flips, incrementing the skip, it's all super, super, super easy. But I spent quite a while just sort of staring at the screen thinking about the right way to do a twist. It would be stupendously easy in, say, Python, I think. Because you can modify an array in place, or I guess they call it a list, you can modify a list in place. You have slices that let you like get right through views of a subset of an array. It's not clear to me exactly how you would handle like the wraparound at the edge of the list, but it doesn't seem like it would be that hard. And you know, being able to mutate all this stuff, random access, all of these are properties that Haskell lists do not have. And while certainly we could use a Haskell array, it's the kind of thing that I don't like do very much, and I would have had to look up how to do it. And it doesn't seem like it's fundamentally impossible with a list. And indeed, it's not. And there's a few nice properties of using a list. For example, the cycle function. Take 10 of cycle 1 to 3, for example, right? We can get an infinitely long representation of view, I suppose, of a list where the end points back to the beginning, which is perfect for these circular lists we're working with, right? So if we can figure out how to perform the operation we want in the context of a linked list, we'll have the advantage that we can rely on a cycle of that list to make it appear infinite and handle wraparound at the edges easily. So my idea was, well, I had two sort of ideas, one of which didn't really pan out. I couldn't see how to finish it. But my thought was, what if we could create two lists, one which is just the input, basically, and another which is the reversed input somehow. And then like zip those two lists together with a function that, based on the index, decides whether to take the original list or the flipped list. And that sounds nice, but I didn't really see any clever way to do it except by producing a list that was just like a correctly twisted list to begin with, and then the zip with function would just be like, oh, take every element out of the second list. So I didn't make progress on that. So what I decided to do instead was basically to twist the list rather than trying to figure out how to do it at an arbitrary position in the center or in the middle of the list. We start by rotating the list around until the beginning of the list is the point that we are twisting. And then after we do the twisting, we put it back. We rotate the rest of the way around so that the elements are back in the positions they started in, aside from having been reversed, some of them being reversed. So I'll explain how this function accomplishes that algorithm. First, though, I want to talk about this ls type. I spent quite a while working with just an ordinary list of int, and it was kind of awkward. I had to call like length on the string a lot of times, and it felt pretty dumb to me. Like, the length of the string was never changing. It's always 256. I could have just hard-coded 256, but I was like, oh, you know, what if part 2 is like, do it with a list of 1024? I didn't want to do that. So what I did was I defined a type here, a length string. I don't know what the right word for it is, but it's just a pair of like a list and a length. And I build one of these once at the beginning, and then instead of passing around a list of int, I pass around a list of int and its length, which is always 256, you know. Which means, remember, calling length on a list is it's expensive in Haskell. You have to walk over the whole list, and so we don't want to do that all the time. So we pull apart the list into its length and its actual component items. And so loop is, we start by defining loop, which is where we do the thing I was talking about. I first cycle the input list, so we get an infinitely long wrapping view of it. And then we drop as many items as necessary to get us so that we're looking at the place where we start, where we're starting our twist. And then flipping that part of the list is relatively simple, I think. We first reverse the first length items of the loop that we have, and then we add to that the result of dropping the first length items of the list that we have. Now we have like an infinitely long list where the first few items are reversed, and then the rest is like what the original string looked like. And notably, it does not wrap around properly. If you walk all the way to like the 257th element, it won't have been reversed, which is why we now just take the actual length. So now we have a string that is just 256 items long. We sort of chopped it off at the end there. And we'll cycle it again in a minute to make it. So, okay, so now we've got that. We've got a string that is 256 long, and it is correctly, all the items in it have been flipped, but it's offset, right? We spun the string around to be looking at the right part of it, and now we need to wind it back to where we were looking at the beginning before the function was called. So what we do is we take flipped and we cycle it again to get a wrapping view of it. We drop the length of the string minus the start position items. This is sort of the same as say the length. Say the start position was 10. We spun the string forward by 10 before we did stuff, and now we're dropping 246 items from the list, which is, spinning it 246 forward. Well, that's the same as spinning it 10 backward, right? Because of circles and modular arithmetic and all this great stuff. So this is undoing the spinning around that we did at the beginning, and now we just take the length, take that many items from the length, so that we just have a normal string again. And finally, we wrap that up in our ls constructor, just passing it the same length. The string has not changed lengths. And so this is sort of like the whole core of the whole puzzle, really. There's a little bit of like supporting mechanisms around it, but like the plan is just to take a state, which is like where we are, what the string is, what parts of it we're looking at, and so on, and just fold a function that updates the state for each length that we have. And indeed, that's part one. We just call fold step of init state, where init state is a new state of 256. So here's our state. It's just a string, the index that we're currently pointing at, and what our skip size is. So we're just going to fold updating that state over each of the lengths. Oh, and I guess I didn't read the part that asks you like for what is the answer. Basically, you just multiply together the first two items in the string when you in the string, I guess, when you're done. And the step function is pretty simple. We just take apart the state object into its length component and like the offset and the skip. We call twist on the string. We add the length and the skip to our offset, making it wrap around by using mod. And we add one to skip. It's like super easy, super simple. And ta-da, that works. And why not? Let's run it, right? All right, whatever. Why is hello? Okay, buttons were not working there. So I actually compiled the main program just in case this was going to be slow. And it produces like a number. This is the right number. And of course it also produces the part 2 input. Oh, actually, I guess I could have. So I've checked out. I thought. Oh, I didn't update. Very funny. I meant to check out just part 1 for you guys, which is what this is. Now part 2 is empty. Okay, great. So let's go look at what part... Oh, of course, we had to parse the string. It's just like... This is a part of parsing in Haskell that I don't feel very satisfied with. I feel like split a list every time a predicate is met is like something that should be built in somewhere, and I just like cannot find it. And so I always have to implement it myself. Of course, with parsec, it's very easy, but you know, that seems like a big dependency to bring in just for like split at commas, right? So anyway, what I had to do was write a split function, which I've written like a billion times. Split calls break. So break is a function that takes a predicate and a list and returns to you a tuple of all the items from the beginning of the string until the first one where the predicate is met. And then the second part of the tuple is all the items after the predicate was first met. So basically you can use this to scan through a list until a condition is met and get the items from before and after that split. So we just basically write a recursive splitting function. We split things up at the first comma, throw away the comma, and return the first item cons to splitting the rest of the items. And if there is no comma left, then the string must be empty, and we just return none. Finally, we map read. Actually, this could just be map. I don't need fmap. We just map read over split. Actually, I'm going to leave that alone because I'm about to get checkout, and I don't want to have local changes. But fmap and map's the same thing. Okay, great. So now let's get back to get checkout master, and I'll show you guys what part 2 of the puzzle was, which was more complicated than part 2s often are. Part 2. The logic you constructed forms a single round of the not hash algorithm. Running the full thing requires many of these rounds. Some input and output processing is also required, which I guess is sort of true, but I don't really think it's input. Anyway, first, from now on, your input should be taken not as a list of numbers, but as a string of bytes instead. Now, this was actually a change that surprised me. I feel like this is the first time that we've been asked to like completely change the meaning of our input. Seems weird, but okay, sure, why not? Convert characters to bytes using their ASCII codes. This will allow you to handle arbitrary ASCII strings, and it also ensures that your input lengths are never larger than 255. For example, if you are given 1, 2, 3, you should convert it to the ASCII codes for each character, 49, 44, 50, 44, 51. Where, of course, these are the ASCII codes for numbers, and this is the ASCII code for a comma. Once you have determined the sequence of lengths to use, add the following lengths to the end of the sequence. And he gives us 5 things. I don't know why these 5. Are they the same for everyone, or what? What meaning do these have? Are these meaningful? Actually, I am curious. Are these meaningful ASCII characters that mean something? They don't look like it. 17 is a very weird one to see. But I do want to find out. So let's... How do I... Here we go. Back to this. Sure. I wanted to see what is map data.bits.char over this. Oh, is it not in data.bits? Where the heck is... There's a function... It is. I just have to say import. Okay. What? It exists. Oh, it's in data.char, not data.bits, you weirdo. Okay. Okay, so these are not meaningful characters. You know, \d is a control character. Like C1, SIT TB are the ones that are meaningful. Oh, and there's a slash. C1SI/TB and then some control characters in the middle. I don't think that's meaningful. Okay. Just curious. Here we are. So we add those. Second, instead of merely running one round like we did above, run a total of 64 rounds using the same length sequence in each round. The current position and skip size should be preserved between rounds. Once the rounds are complete, this just like keeps getting more complicated, you'll be left with numbers from 0 to 255 in some order, called the sparse hash. Your next task is to reduce these to a list of only 16 numbers called the dense hash. To do this, use numeric bitwise XOR to combine each consecutive block of 16 numbers in the sparse hash. And of course, since we have 256 numbers, there will be 16 such blocks of 16. So we XOR them all together. Blah, blah, blah. We all know how to XOR things. Finally, the standard way to represent a NOT hash is a single hexadecimal string. The final output is the dense hash in hexadecimal notation. Okay, fine. So, how do we do it? We didn't really have to change any of the stuff that we used for part 1, which is nice. I needed eventually this function here, which I think is in data.list.split, but I forget if that's a real package, or I think it's like a dependency you have to install, and like it's relatively simple, so I just wrote it. Where you take a chunk size and you say, give me all the chunks of this size from a list. Pretty simple. You just take that many things and cons the result of recursively calling blah, blah, blah. And also a function from int to string that converts a string to hex. There's a function in data.char called int to digit, the opposite of digit to int that we used before. And conveniently, it works not just for numbers 0 through 9, but also A through F. So we just write, wait a minute, this is such a weird way to do it. What I should have done was this. Int to digit of x divided by 16, that's the first character, and int to digit of x mod 16, that's the second, and put them together into a list. And since a string is a list of characters, we don't have to do any weird conversions. We just say, here's the list of characters, and it's also a string. Finally, part 2. Actually, I had to make a change to main here, where I moved the parse function, which was here, because I figured we'd want to parse the input for all things. Who knew? Turns out you don't want to. I attached it to part 1 instead. And for part 2, an equivalent parsing function is map_ord, where ord is the function that takes character and produces the ASCII code for it. Its ordinal number. And that makes from there, part 2 is pretty simple. We just take the lengths and we add this special code to the end of it for some reason. And then, rather than like having a function for like running a single round over the lengths and then another function for folding that over 64 times, I just take the length list and append it to, expand it out 64 times and treat that as one single very long round, since you're supposed to carry everything over between rounds anyway. With replicate, which takes an input, here, replicate 5 of x, does sort of what you expect. And then we can cat it all together to flatten it into a single list rather than 64 lists of however many items. We compute the sparse hash by folding step over make state of 256 and the rounds, basically what we did in part 1. And then we compute the dense hash by mapping a fold of XOR over each chunk of 16 items in the string of the sparse hash. And then we map, we bind hex over that, which we talked about before. For lists, bind is map and then concat. So we map hex over each chunk of the dense hash, we concatenate the results together, and we have a string that is the result of calling hex on each of the dense hash chunks. And I wanted to change this fmap to just be map, since it was sort of, oh my gosh, I'm just typing random garbage. Okay, and if we stack GHC, very nice. Run the, oops. It in fact runs very quickly. I wonder, actually, how long would it take? Oh, GHC would be better than GCH. Yeah, so it doesn't take any particular time, even without compiling, but I wasn't sure, so I compiled it. And there you go, there's our dense hash, 9DE88, blah, 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 blah. I copied that and pasted it, and it was the right answer, and we were all very happy. So any more thoughts to share on this? I don't know. I'm not so keen on this. Like, I don't know if it would have been a better choice to use an array instead. On the one hand, you know, being able to treat the list as circular was kind of nice, which you couldn't really do with an array. But on the other, it's like kind of complicated, and I don't know. I guess you really, if you had an array, you could sort of treat it as circular pretty easily by just using modular arithmetic on all the indices you're using. I think an array is probably a better way to solve this than what I did. Because we have all this taking and dropping, and we have the convenience that we can use a cycle, but it involves a lot of extra work to make that fit. So probably would have been better to just use modular arithmetic on an array, but then I'd have to look up how to use arrays and blah, blah, blah. So I don't know. Anyway, that is it for this episode. Thanks for watching, and I'll see you next time.